Welcome to the deep dive. We're looking at a really intriguing puzzle today, something called the TeraZ mirage.
It's this idea about future particle colliders, the electron-positron ones, planned to run at the Z-pole. We call them TeraZ collectively.
And they're designed for incredible precision, aiming to find hints of new physics by spotting tiny deviations in measurements.
But the mirage part is, what if that new physics is hiding? Right there in plain sight, but invisible to these precise probes.
That's the core concept, that even with this amazing precision, new particles, new forces might just stay hidden because of, well, blind spots in how we analyze the data.
We call them blind directions. There's specific ways, parameters in our main analysis tool, the Standard Model Effective Field Theory, or SMEFT, can combine.
Combine in such a way that our super precise Electroweak measurements, the main output of TeraZ, just aren't sensitive to them. It's quite surprising.
And it's not just some theoretical quirk within SMAFE itself. The key point is that these blind directions can actually pop up quite naturally.
Naturally from what, though?
From realistic theories that go beyond the standard model. Theories that include multiple new, heavy particles we haven't discovered yet.
So our mission here is to explore how these blind directions come about in these more complete theories, and really what it means for TeraZ. Can it actually make the discoveries it's designed for?
Let's start with SMEFT. It's really the standard language now for interpreting potential deviations from the standard model at the energy scales TeraZ will operate at.
Its strength is that it's model independent, right? You don't need to assume a specific new theory from the start.
Precisely. It parameterizes potential new physics effects in a general way, but it's a very large framework.
Large how? Compared to, say, the effective theories used in flavor physics.
Much larger. SMEFT at dimension 6, the level we usually consider first, has 2,499 independent parameters or operators. Compare that to the low-energy effective theory, LEFT, used in flavor. It's a huge difference.
And this vastness, these thousands of parameters, that's where the problem lies.
It allows for possibilities. Possibilities for different operators, different potential modifications to the standard model to effectively cancel each other out.
So their combined effect on the specific things TeraZ measures, these Electroweak precision observables, could be zero or very close to it.
That's the idea behind these blind spots.
Yeah.
You could have significant new physics happening, described by several SMAFT operators, but they conspire to leave almost no trace in the specific measurements TeraZ is best at.
It makes the new physics invisible, effectively.
There's even a historical precedent for this kind of thing. Remember LEP, the Large Electron-Positron Collider?
Before the LHC, yes. Famous for its precision Z-pole measurements, too.
Well, LEP's precision data couldn't actually rule out a whole extra generation of fundamental particles, a fourth family of quarks and leptons.
Really? Why not?
Because of a blind direction. The way that fourth generation would have affected the measurements allowed for cancellations. It was only later, with Higgs measurements at the LHC, that the idea was firmly excluded.
So it shows that indirect searches using precision measurements have inherent limitations. They can miss things.
Absolutely. Now, our work focuses particularly on a class of SMEFT operators called 4 fermion operators.
Interactions involving 4 fundamental particles at once.
Yes, and these are very common in many proposed extensions of the standard model. They often get generated right away when you introduce new heavy particles in a theory.
And you focused on interactions involving the third family. Top quarks, bottom quarks, tau leptons.
We did, partly because there are theoretical arguments suggesting new physics might couple more strongly to the heavier particles. It's a common theoretical expectation.
So what specific blind directions did you find involving these operators?
We found several. One clear example involves 2 Wilson coefficients, these numbers that quantify the strength of specific operators. They're called CEE and CGT.
Describing interactions between different types of quarks.
Yes. And we found that if these coefficients happen to be roughly equal, so COED is approximately the same as CFOD, then the sensitivity of the Electroweak precision data just plummets.
And this isn't just a coincidence at one specific energy.
No, we checked that. We included the effects of how these coefficients change with energy scale, the renormalization group evolution, and the blind direction persists. It seems quite robust.
Are there others? More complex ones?
There are. We identified another interesting one involving 4 different operators, CEU and CUG.
Those involve electrons, quarks, and leptons. Quite a mix.
Indeed. The blind direction here occurs if there's a specific relationship, roughly similar to CU, and both similar to plus or minus 6 day, and also plus or minus x key.
That sounds like quite a specific tuning required between different types of new physics effects.
It is. It highlights how intricate these cancellations can potentially be.
What about higher order effects? Could quantum corrections within SMFT itself spoil these cancellations?
We looked at that too, specifically finite, one-loop corrections within the SMEFT framework.
Do they eliminate the blind directions?
They don't fundamentally change the picture. They might slightly shift the exact numerical relationship required for the direction to be perfectly blind, but the regions of insensitivity remain. The blind directions seem to survive these corrections.
So the blindness isn't just an artifact of the simplest approximation.
It appears not. Which brings us back to the ultraviolet completions, the actual theories with new heavy particles.
How do these directions arise from those theories?
Well, when you have a theory with new heavy particles, and you want to describe physics at lower energies, like at TeraZ, you integrate out those heavy particles. You drive an effective field theory, like SMEFT.
And the process of integrating them out can generate these specific combinations.
It can. Sometimes a single new particle might generate just one SMAT operator, maybe one that isn't part of a blind direction. We identified several examples, fields like CDT, B, WT, L3 dollars, and others that generate operators like L dollars, which are generally well constrained.
But for the blind directions you mentioned,
For those, you typically need multiple new particles interacting in specific ways.
such as for the SIMC1 direction,
Yes, that one seems to require combinations of fields. For example, pairing a scalar like LAD or Fenrir with a vector boson B dollar or G dollars, or pairing leptoquarks like gamma naught or omega dollar with other leptoquarks Q dollar or Y dollar.
Right.
Specific pairings are needed.
and the more complex four-operator direction.
That requires even more specific setups, typically involving 5 new fields in particular arrangements. We found combinations like omega-1 Q5 or U5 dollars paired with other sets like PAM LAD, omega-1 XT, or Q11 X zeta, among others.
So the point is, these aren't random combinations in SAFT. They can be the direct consequence of specific, albeit sometimes complex structures in a more fundamental theory.
Exactly. To illustrate this, we built 3 concrete models with multiple new particles.
And checked if they generated blind directions.
Yes, Model 1 had 2 leptoquarks, omega dollars, and Q dollar 1. We showed how certain relationships between their couplings and masses naturally lead to a blind direction, which is poorly constrained by Electroweak precision data.
Model 2.
That one had a second Higgs doublet, beta dollar, and a heavy W prime boson, bottle ever. Again, we found a blind direction linked to their properties.
And importantly, you checked the impact of integrating them out more carefully. One-loop matching.
We did one-loop matching calculations for integrating out the heavy scalars in these models. The result was consistent. The blind directions identified at the simplest level, the tree-level matching, were not removed by these loop corrections.
What about the third model? Did it generate the four-operator direction?
Yes, Model 3 was designed to do that. It involved 5 different leptoquark fields: omega-1U, T-Midgelized-4E, PSCC, T56, and $6.
A more complicated setup.
It is, but it showed how the relationship SIMC-Z could arise from specific relations between the underlying leptoquark masses and couplings. And again, loop corrections didn't spoil the blindness.
So these examples really drive home the point. Blind directions aren't just mathematical oddities in SimCT.
They seem to be genuine features that can arise from well-motivated extensions of the standard model, particularly those with multiple new particles. And they appear robust against higher-order corrections in the matching process.
The crucial takeaway then seems to be, well, that the sheer precision of TeraZ might not translate directly into sensitivity to all kinds of new physics.
That's the concern. The number of precise measurements is huge. But if the new physics lies along one of these blind directions, that precision doesn't help as much as you might initially think. It could overestimate our reach.
Which implies that relying only on TeraZ's precision electroweak measurements could be insufficient.
It might not be enough to rule out significant classes of new physics models, simply because those models naturally hide in these blind spots of the parameter space.
So what's the path forward? How do we overcome this?
This really highlights the need for complementary experiments. High-energy colliders, like the high-luminosity LHC or maybe future hadron colliders, probe physics in a different way.
They operate at higher energies, obviously. How does that help break the blind directions?
Because the effects of SFAFT operators often grow with energy. A cancellation that holds perfectly at the Z-pole might be broken at higher energies, revealing the underlying new physics. High-energy machines provide a different crucial window.
It emphasizes the synergy needed between different types of experiments. Precision isn't everything if you're blind in certain directions.
Absolutely. Which leads us to the final thought for you, the listener. Given these inherent limitations revealed by the TeraZ Mirage concept, what other approaches should we be pursuing? Are there different experimental techniques, or perhaps entirely new theoretical frameworks beyond the SMEFT that might be essential to finally uncover what lies beyond the standard model?
A critical question as we push the frontiers of particle physics. Thank you for that deep dive.